Hello everyone. In this video we are going to look at thermal stress in material. And by thermal stress we mean that the material cannot move, it's constrained mechanically. So when the temperature increases or decreases, it has the thermal expansion or contraction, and since it cannot move, there will be some forces and some stress in the material. So it's thermally induced stress basically. Now you know that if you have some material with the thermal expansion coefficient alpha, the temperature increase is delta T and length is L. The change in the length is delta L equal L alpha delta T. So the strain due to that, which is delta L over L, is going to be alpha delta T. So this is the strain due to thermal expansion. And now, if the material cannot move, then there will be stress, and it works, of course, in the linear region. So here we assume it works in the linear region. So normal stress is E times normal strain, and we replace that here. So the stress induced in the material is going to be alpha E delta T. Now it looks very simple and very easy, but when we solve problems, they might not always be that easy. And here is an example of such problem. So here we have this sleeve in blue, and it is basically, it's a tube here with length L. The cross section of that is A sub S, okay? And the length of it is L, as I said. Now on both sides there are washers, and then there is this long bolt and the knot, and the sleeve is restrained by the bolt, knot, and the washer. Now the bolt has cross section A of bolt, and it has the effective length of L as well. That is under pressure. This portion of it is free, so we don't need to count that. The alphas for the material for sleeve and bolt are different. For the bolt is called alpha bolt, and for the sleeve is called alpha sleeve, and alpha sleeve is bigger than the bolt. Okay, so alpha sleeve is bigger than the bolt, which means when you put them under the same temperature change, the sleeve wants to expand more, but the bolt is not going to let it happen. And for that reason, there will be basically compression in the sleeve and there will be tension in the bolt. Okay, and we want to first of all find these stresses, sigma S and sigma B, the stresses in them, and the change in the length of the total system, delta, and then see what happens if they were made from the same material, which basically means these two were the same amount. Okay, what would happen? So here, in order to look at that, what we do is we first remove one side of the constraint, the same thing we did with statically indeterminate. Remember when we solved this example in my previous video, this one, in order to be able to solve, I took off this portion, correct, and then replaced it by the force of it, and we could solve the problem. So here we have to do something similar. And we get rid of this constraint on the right hand side and set it free. Now if we set it free, what's going to happen? Let's say this head is not there and this washer is not there. Well, of course, since they are free to expand, the sleeve will expand by delta 1 and the bolt will expand by delta 2. Clearly delta 2 is less than delta 1 because alpha S is bigger. Now first thing is, how much is delta 1, how much is delta 2? Clearly delta 1, which is the change in the length, we go and use this formula that we had, correct? So for both of them, the length is L. Now delta 1 is for the sleeve, so it's going to be alpha of the sleeve, correct? And then delta T. And similarly, for the bolt, delta of bolt, or delta 2, is L alpha of the bolt times delta T. And clearly, delta 1 is bigger than delta 2. Because the alpha is bigger. Good. So now what's going to happen? Now here is the part that we have to bring the effect of that bolt and that washer and force them to both basically expand the same amount. Why? Because if not, if one of them expands more than the other one, now initially they do, of course, if we take away the effect of the head of the bolt. This one expands more, but remember, these two should have contact. This bolt, this washer, should always have contact with the sleeve here. So the forces that are created inside the two material, the effect of those forces is to make the total elongation of both of these to be the same. In this case, we call that total elongation for both of them, which is the same. We call it delta. So what happens here? Because the sleeve is expanding more, the bolt is going to push back on it. So there will be some force on this sleeve, which here we call it PS. And this PS is going to create compression, and compression will shrink down delta 1. So delta 1 is going to go back by the length delta 3, okay, and becomes the final delta. On the other hand, the bolt will be under tension, and that tension force, we call it PB, and that force will make the bolt expand a little bit further by the amount delta 4, such that that also goes to the length delta. So I can say that delta, the equivalent elongation for both of them for the sleeve, equals delta 1 minus delta 3. Delta 1 is the thermal one, delta 3 is because of the compression. For the bolt is delta 2, again the thermal one, plus delta 4. Delta 4 is the one due to tension. Okay, yep. So if we move on, now delta 1, there is a formula for that. So delta 1, we have it, L alpha S delta T. The question is, what is delta 3? Delta 3 comes from the force PS. So we have to divide the PS force by the cross-section AS. That will give you sigma, correct? And then multiplied by what? Multiplied by L divided by E. So that is sigma divided by E. That's epsilon multiplied by L. That is what? That is the compression, the elongation due to compression. And this is the formula we learned in my previous video, axial deformations. Now delta 2, we have the formula again, alpha L alpha S delta T, alpha B delta T, I'm sorry. And plus, now delta 4 is similar, this time it's PB L A of bolt and E of bolt. Remember, the Young modulus are different because they are different material. So now if you look, this is clearly one equation between them. I call it equation 1. How many unknowns are in this equation 1? The unknowns are PS and PB. Everything else is a given parameter. Okay, so the forces in these two members, I don't have it. Now, if I look at the free body diagram, what can I see here? Well, if all I need is to look at the washer on this end. If I look at that washer on this end, the forces that are acting on it is one force coming from the bolt, right? The bolt is going to be extended, correct? And the sleeve is going to be, so if you look at this is the head of the bolt, right? So clearly the sleeve that is right under the washer is going to be forced back. So you're going to get the force like this, which is PS, and the bolt is going to go this way, as you can see. And since this is a static scenario, clearly from equilibrium, PS has to be equal to PB, otherwise it will mechanically displace, not just deform. So here, this is equation 2 that comes from the free body diagram. Now from 1 and 2, if you replace, you should be able to solve for both of these unknown forces. So if I solve for them, I am going to get, well, since they are the same, so there is only one solution. They are equal to, it is going to be alpha S minus alpha B times delta T times ESAS EBAB. This whole thing divided by ESAS plus EBAB. So this is the force in both of them. One of them is compression, the other one is tension, but their magnitudes are equal. And so this is the first part of the problem, which is asking what are the sigmas. Now for sigmas, all we need to do is to divide them by the area. So clearly sigma in the sleeve is force in the sleeve divided by AS, and sigma B is force in the bolt divided by AB. So clearly they're going to be the same as this, except the AS or AB is basically eliminated. So if I go down here and copy paste this down here, all I need to clean up is the AS part, which is this portion here. And if I do it for this bottom one, again, so if I pick this and bring it right here, again, the only thing I need to cancel is AB, which is this. Done. Okay, so this is the answer to the first part of the problem. What are the stresses in the bolt and in the sleeve? These guys. Then in part 2, it says what is delta? What is the equivalent elongation in both of them? Well, all I need to do is to go back here, and then on one side of this, when I found PS or PB, I either go for left side or the right side. They are the same. If I do that, here I use the left side, and if I go for that, I am going to get alpha SEAS AS E of SAS plus a similar thing for bolt. And then the whole thing multiplied by delta T and L, and divided by, again, ESAS plus EBAB. Now it says what happens if the alphas are the same. Well, clearly you can see if the alphas are the same, right? So if alpha S equals alpha B and ES equals EB, so they are from the same material, what's going to happen? Well, clearly both of the forces are going to be zero, both of the stresses are going to be zero, and the elongation is going to be easily simplified to how much? Well, if you do that, you are going to get basically alpha delta T times L, which is assuming that they are from the same material. So these are both equal to alpha. Okay? And you can easily simplify that here, because this one, you can see that this one in the numerator, alpha and E are the same. So you factor it out, it's going to be alpha E times AS plus AB. And in the denominator, E's are the same, so it's going to be E times AS plus AB. And these would cancel, and you're going to get alpha delta T times L. So you see that although the formula looks very simple and so on, it doesn't necessarily mean that the problem is super easy. Now, it's not hard, but it's not trivial, and you have to work through what you learned previously for axial load and this new one, thermal stress, and then solve this problem. So hopefully the video was useful to you. I'll see you in the next lecture.